Hi everyone, welcome back. We're going to talk today about descriptive statistics. And this is really also part of getting to know your data. It's running some basic descriptive statistics to get to know what's in your sample, to summarize what's in our data. So the two main categories of descriptive statistics are measures of central tendency, or center, and measures of variability, or spread. So when we think about a histogram or other distribution, we can think about there being a middle point in the distribution. We can also think about how spread out it is, right? And there are ways that we can quantify the center point and also to quantify how much spread there is or how much variability there is in our data. So we're going to distinguish between measures of central tendency and indices of variability. And we're going to relate those terms to describe the frequency distribution that we see when we run a frequency distribution in terms of modality, so how many peaks it has, its symmetry, skew, and kurtosis, which we're going to cover. We're going to define and describe descriptive statistics, correlations, scatter plots, and correlation coefficients. So these are all descriptive statistics that allow us to summarize our data using either a single number or a smaller number of numbers to quantify what's in our data, to summarize what's in our data. So descriptive statistics are used to describe a sample, a study sample. And today we're just going to look at things that we would use to quantify or calculate measurements that describe what is in our data. Now, in a research paper, the first table that we would report would often be a summary of some of the descriptive statistics that we're going to describe today. But it also is an important first step in the research process where you're trying to get to know your data and you want to understand the range of values that occur, what is the mean, what is the median, and things like that, which we're about to get into. Starting with the sample mean, it's the most frequently used measure of central tendency. You've all calculated means before. Mean is just the same as the average of a set of observations. It looks a little scary here, it looks like a big formula, but basically what this is saying is that the sum of our observations on some variable x or something that we're measuring x is the sum of those values divided by the number of observations, and that gives us our sample mean. Okay, so it looks like a fancy mathematical symbol, but it's really just saying the sum of all of our observations divided by the number of observations. You've done this all before. Values of an interval or ratio variable are summed and divided by the number of observations. So again, a sample mean would not make sense for an ordinal measure or for a nominal measure, but we would use that for interval and ratio measures. So here's an example, and this is a very small study with 7 observations, but just for purposes of demonstrating calculation, we have these different ages, 27, 27, 26, 29, 28, 31, and 30. So we have 7 observations. We would simply just total those values, divide it by the number of observations, and then we have our mean. I told you that was not really a scary formula. And actually all the formulas that we present in this course are really just statistical notation so that you are familiar with it, but the calculations themselves are relatively straightforward. We're not doing anything more than multiplication and long division. So if you see symbols that are unfamiliar, it's just the way statisticians tend to write things out. The sample median is the score that divides the distribution into 2 equal halves when ordered by rank. So once we've ordered our values by rank, let's say from lowest to highest, we're going to pick that value that's right in the middle. Okay, so for that last example where we already calculated a mean, we happen to have 7 observations. So there's a value that's right in the middle, which is 28. And notice that I sorted that from lowest age to highest age. Okay, now that may not exist in your data set that way. You'd have to arrange it that way or have the computer determine what the median is. But in this case, 28 would be our median value with 3 below it and 3 above it. So here's another example with a slightly larger data set of 10. In this case, we're looking at blood pressure, and our blood pressure readings are range from 62 to 81. Now, in this case, the middle value, because we have an even number of observations, 10 observations, it actually falls between 70 and 72. So it doesn't actually occur as an observation within our 10 samples, but the middle value would be 71. We'd have half of our values below and half of our values above. Okay, so if you run into a situation where there's an odd number of observations, the median is simply the middle value. When there's an even number, like we have here, the median is the mean of the two middle values, the two middlemost values. So here we had 70 and 72. The average of those two would be 71. So that's how that was derived. Pretty straightforward. But again, your data wouldn't necessarily be sorted from highest to lowest. So we would normally ask a computer to derive the median for us. With a smaller sample like this, it's easy enough for us to do it ourselves. This gets us to the sample mode. And I know mode sounds a lot like median and sounds a lot like mean. They all start with M, so I didn't make up the names for these, so don't blame me for getting them confused. But mode is the most commonly observed value in the data set. The mode is a little harder to get your head around because the mode isn't always as interesting as the median or the median. And we don't often report out modes as often anyway as we do means and medians. It's relatively easy to derive the mode by simply looking at our frequency distribution and finding the highest count. And unlike the mean and the median, the mode is always going to be an actual observed value in the data set, right? So a mean, when we calculate a mean, it could be actually a decimal, maybe average. Median could be a value that falls between two values. The mode is the value that actually had the highest number of observations. So it can be hard to think about times where mode would be interesting, but here's one example. We have age and initiation of smoking among adolescent smokers. So these are kids who already smoke. What age did they initiate? So the mode here is the value 17, age 17, where we have the highest number of individuals who reported smoking at that age. Notice there was also a relatively high value for age 13, but our mode here would be age 17, which had the most commonly occurring value. And that could be interesting if you were planning an intervention and you wanted to know what age is the most likely that someone will adopt a behavior like smoking. And it could correspond to the mean and the median, but it could be a value quite far away from the mean and median. So it can have some clinical or public health relevance, but it isn't often reported as mean and median. Okay, moving on now to our measures of variability and spread. Variability concerns how spread out or dispersed our data values are in a distribution, right? So if you think of the range of heights of just the general population, they're going to be really spread out, right? Relative to, let's say, NBA basketball players, where the range will be much narrower in terms of height. You're still going to have some who are 6'2", maybe 6 foot, up to, 7 foot something. But the range is relatively restricted among NBA players. But if we talked about the overall population, it would be more spread out. So we want to describe how much variability there is in our data. Two distributions with the same mean could have very different amounts of dispersion around that mean. And so it's another way of describing our data, how much variability there is in our study sample. There are multiple indices of variability. They include the range, the interquartile range, the standard deviation, and the variance. Of these, the standard deviation is going to be the most important in terms of going forward and understanding variance, but we do often want to report out things like range and interquartile range. So let's define those. The range is the difference between the highest and the lowest values in a distribution. And again, I've conveniently sorted this from lowest to highest value, 110 to 190, and we have our weight in pounds. The range here would simply be the difference between the highest value, 190, and the lowest value, 110. So the range value would be 80. So an informal way of talking about range would say the values go from 110 to 190, but the calculation of a range would be 80. So the range of age, or the range of weight in this case, would be 80. It's relatively easy to compute. All I have to do is know the lowest and highest values. It's readily understood, although it could be more informative if we anchored it to values. But it does communicate information of interest to readers to report. So if we were looking at a study of cancer, you could simply look at the range and determine, did this sample include a wide age range, or was it a relatively narrow age range that was included in the study sample? The disadvantages of the range does depend on only 2 scores and does not take into account all information. So it wouldn't necessarily weight in data points. It would simply take those lowest and highest values. So it is very sensitive to outliers, extreme values. We could have had one observation that was well outside the range of the typical values. It tends to be unstable and fluctuates from sample to sample depending on who we've included in our study. And it is influenced by sample size, again, in terms of which values are going to be occur in our data. If we have a really small sample, we may not have those more high-end values or low-end values just by the nature of the sample size. The interquartile range is based on first dividing our data up into quartiles. Quartiles is dividing our data into 4 groups. And we designate quartile 1, quartile 2, and quartile 3. Quartile 1 is the point at which 25% of scores or values fall below the first quartile. The upper quartile, quartile 3, cuts off the upper 25%, and 75% of the scores fall below it. Okay, so to compute the interquartile range, we simply take the value of quartile 3, subtract quartile 1, and that gives us our interquartile range. Okay, and we would often do this with values that don't have a normal distribution, and it doesn't make sense to calculate a mean. So we can interpret the interquartile range as the range of scores within which the middle 50% of values lie. Okay, you will see interquartile range sometimes reported with the actual values of quartile 1 and quartile 3, but technically the interquartile range is like the range, a single value. So here again, we have weight divided into quartiles, where quartile 1 would fall at 130, quartile 3 would fall at 170, and the median would actually be 150. But we don't need the median to compute the interquartile range, but I just wanted to display where that was. So quartile 3 minus quartile 1, or the value 170 minus 130 would equal 40. Okay, so like the range, it simply quantifies how spread out the data are. In this case, it's where 50% of values fall, whereas the range would have been the entire distribution. Some advantages of the interquartile range is it reduces the influence of outliers and extreme scores in expressing the variability. Again, it's taking that middle 50%. It uses more information than the range. And it can be important in evaluating outliers. So if we start to have values that are well outside that middle 50%, there can be rules that are set up to identify those outliers. Disadvantages, it's not particularly easy to compute. A lot of people don't understand the interquartile range, nor do they know how to report it, as I mentioned. And it doesn't take all the values into account. So those are some disadvantages of the interquartile range. You do see it reported often in research papers, but it's not always that informative. A box plot is a way to display the quartiles within a distribution, sometimes called a box and whiskers plot, which is kind of a cute name for it. It's a graphical display that shows the median, the interquartile range, and the highest and lowest non-outlying values. You can also ask that it plot outlying values on the box plot as well. And outlying cases can be shown where you have mild outliers, which are 1.5 times the value of the quartile 3, or 1.5 times the value of quartile 1, or in the case of extreme outliers, it'd be 3 times the quartile 3 value, or 3 times outside the quartile 1 box. And so here's an example of a box plot of heart rate, and you can get the software to do this for you. You're not drawing this by hand. And the number of values here, there were 15 observations. The upper limit was 76. That was the highest value that was not considered an outlier based on those criteria which I just mentioned. We have a median value of 64. Quartile 3 is 68, quartile 1 is 55. So you can see that box corresponds to the interquartile range. The lower limit value is 45. Okay, so it's plotted the interquartile range, the upper limit, the lower limit, and then any value that fell outside those boundaries that we described as being an outlier. Okay. This is the more important measure. We're going to use standard deviation a lot in this course. The sample standard deviation is an index of how much, on average, scores in a distribution vary. Okay, so this is for variables that we're quantifying how much do scores on average spread about their mean. So standard deviations are based on deviation scores calculated by subtracting the mean from each observation's original score. So positive deviation would be a score higher than the mean. A negative deviation score would be below the mean. Because there are both negative and positive values that are spread evenly from the mean, when you add up the negative and positive values, it would always sum to 0. So to calculate the standard deviation, and because of the presence of negative deviation scores and positive deviation scores canceling each other, we would calculate it by first taking those differences between each observation and the mean, and then squaring them. But squaring them, we're making them all positive values. Negative times a negative is a positive, positive times a positive is a positive. So and if we take those squared values and then sum those, we can then take an average of those squared deviations from the mean, okay? And that's what's represented in the formula here. We're not done yet, okay? We've squared all those values so that we can get them all in the same direction. We've got how much spread there is overall, or the absolute value of spread. We've averaged it out. Now we need to take the square root of that value to get it back into what we wanted, which is the average deviation from the mean. Okay, so it seems like a lot of work, but it's because we had to deal with both positive and negative values. And now we have essentially an average deviation from the mean. To show this more schematically, what we would do if we were to do this manually is we would calculate first each value's difference from the mean. You can see that in the second column. First, we had to calculate the mean, which was 123.6 for this set of observations. So that would be summing up all the values on X, which is 865, and dividing that by 7. And so that's how we got 123.6. Again, we've got negatives and positives, and if we sum that all up, we get this value 0. Okay, so if we square them, we end up with all positive values, and that's what we have here in the numerator in our averaging out. Notice we're dividing by n-1, not by n, okay? And that has to do with the fact that our middle value could actually be part of these values, and so we want to account for that. And so when we take the square root of this much larger number, 374.6, we get our standard deviation of 19.4. So we then say that we have an average of 123.6 and a standard deviation of 19.4, and those are in the same units as the original variable. So the sample standard deviation can most readily be interpreted as the average difference of observed values from the mean. Any observed value can then be expressed in terms of how many standard deviations it falls from the mean, as we're going to see shortly as we calculate standardized scores. Okay, so we've calculated a standard deviation. What do we do with it? Well, it is informative, both in terms of just how spread out the data is, but it also lets us know where values are likely to fall. If we assume a somewhat normal distribution for the variable, and we're going to get more into normal distributions later, but we would typically find that about 2/3 of values, 68% of values, will fall within one standard deviation of the mean, and 95% of values will fall within 2 standard deviations of the mean. And then almost 100%, or 99.7%, will fall within 3 standard deviations of the mean. So the value of the standard deviation can tell us how far away a value is from the mean and how unlikely it is to occur, how common it is within the distribution. This is an important concept that we'll go into later. But the standard deviation is probably the most important measure of spread. Standard deviations can be influenced by extreme values, particularly in smaller samples. It is difficult to hand calculate, as you just saw, and if we had more observations than 7, we really would want to use statistical software or a calculator to avoid making errors. The use of the term standard is not intuitive, but if you think of it simply as the average deviation from the mean, that's what the standard deviation is really telling us. So some advantages: it takes all data into account in calculating variability. Don't forget we calculated deviant scores from each observation from the mean, and those were included in the calculation. It's more stable as a measure of variability than the range or interquartile range, and it lends itself to computations of other measures that were often used in inferential statistics, which we're going to talk about next week. It's helpful in interpreting individual scores when data are distributed approximately normally, as I just described earlier, where most values are going to fall within 1 standard deviation. Almost all will fall within 3 standard deviations from the mean. This brings us to the concept of standard scores, or z-scores, which is a way of expressing a variable not in terms of its original units, but in terms of standard deviation units. So standard scores are an index of relative standing, helpful in interpreting raw scores derived from the standard deviation. It's also called a z-score. This has to do with the distribution that we're going to talk about later, the z distribution, and is expressed in standard deviation units relative to the mean. So a z-score of 1 means an observation is 1 standard deviation from the mean. A z-score of -2 would mean 2 standard deviations below the mean, etc. So it's a way of talking about variability without using the original units. And it then becomes a little more useful for comparing across different measures on different scales, but because you can talk about how different a value is from its own mean without having to think about what the units are. So standard scores can be easily calculated to express how many standard deviations an observation is from the mean. Again, looks like a fancy formula, but all we're doing here is taking the observation that we have, x, subtracting the mean, and dividing it by the standard deviation. Okay, so if we wanted to know how many dozen eggs we had, and we wanted to express it in terms of dozens instead of individual eggs, we would take our original value and divide it by 12, right? So here we are calculating a value, how many standard deviations is it from the mean? So for example, if we had a mean calculated as 100 and standard deviation of 25, if we had an observation where the value of x was 125, okay, it's 25 points above 100, so 125 minus 100 would be 25. Divide that by 25, which is our standard deviation, we get a z-score of 1. If we had an observation of where it was 50, or 2 standard deviations below the mean, okay, so 50 minus 100, 2 standard deviations below the mean. So our z-score would be -2. We can actually have our software do that for us, but it would also be relatively easy to do that computationally, even without that feature. Okay, finally moving on to variance. The sample variance is an important variability concept in inferential statistics, which we'll talk about next week, but we don't often use it descriptively. We actually already calculated it. The variance was that step where we squared all the deviations and then divided it by n-1. But prior to taking the square root of that, that is our variance. And it's a value that tends to be large, but it's the total absolute variation, squared variation. And it's not easily interpreted because it's a squared value. It's not in the original units. But when we start to talk about explaining variance in some measure, we are going to be basing it on these squared differences from the mean. Okay, so in addition to our indices of variability, we can also kind of just describe the shape of a distribution as well. And this becomes important when we start characterizing variables as conforming to a specific distribution in terms of its shape. Does it look like a normal distribution? So we're going to look at things like modality, symmetry, and kurtosis, which are terms that describe the shape of a distribution. I realize these terms are unfamiliar, so I'm just going to quickly go through some of these. We're not going to spend a lot of time on these, but they can be important for identifying situations where we may need to be mindful of needing to use different approaches because our assumptions about the distribution are not being met. So modality describes how many peaks there are in our data set, values with very high frequencies, okay? So we would, in a normal distribution, we'd have a single peak, right? Well, in the case of what I showed you earlier in terms of age of initiation, that almost looks like there were 2 peaks in the distribution, in which case we would call that a bimodal distribution. It may not make sense to think of them as having a singular distribution. We could also use the term multimodal to refer to any data that has multiple peaks. Okay, so that's one measure of, and that's one way of talking about the shape of a distribution is in terms of modality. Symmetry is where we could take 2 halves of a distribution, fold them over, and they would be identical. Okay, so in a perfect normal distribution, it would be symmetrical, like you see here. That's another property of a distribution that we can describe. An asymmetric distribution, or a skewed distribution, where the peak is slightly off center or extremely off center, and there are uneven tails towards either the high values or the low values, can also be important, something that we may need to address when we do statistical analysis. A positive skew is when we have a longer tail off to the right with fewer observations with high values. A negative skew is when there's a longer tail to the left with fewer observations with low values. And the best way to look at this is positively skewed, it's skewed to the right. It refers to where the tail is going. Okay, so that's to the right, it's tailed, it's positively skewed. Negatively skewed or left skewed, the tail is going to the left, okay? It's a little confusing because the bulk of the values here are the opposite of saying left or right or positive versus negative. It's where the tail is going that we're talking about the asymmetry, which I personally find very confusing, but that's important to remember that it's the tail that dictates whether it's left skewed or right skewed or positively skewed or negatively skewed. We're not going to spend a lot of time on this concept, but kurtosis refers to the degree of pointedness or flatness of a distribution's peak. So we could have a value that's peaked very high in the middle, which we call a leptokurtic, or how leptokurtic is the distribution. Mesokurtic would be neither pointy nor flat, and then platycritic would be a flat peak. Okay, and this becomes important when we get into looking at the shapes of distributions. There's actually a series of distributions, the T distributions, which go from having more platycritic shape to a more leptocritic shape, or closer to a standard normal distribution. Okay, so that's where that concept will become important, but overall we don't necessarily spend a lot of time worrying about that. However, it is important conceptually to be able to describe these things and having a language around shapes of distributions. Especially when we get to talking about something like a normal distribution, how much does a distribution look like this normal distribution? We also call it a bell-shaped curve or a Gaussian distribution. And it has some kind of unique properties. First of all, the mean equals the median equals the mode. Okay, you got that peak right in the middle, and all three measures of central tendency are equal. And this is an ideal normal distribution. It's unimodal, notice there's one peak. It's symmetric, we can fold both halves, and it's neither peaked nor flat. Okay, so the normal distribution is really important when we get to inferential statistics, when we start developing what we call probability distributions, or we're using that to make inferences about a population. But for now, it's just important that we understand that there are these terms that we use when we're describing distributions. And normally we're going to be interested to see how much it conforms to a normal distribution, but there are certainly many other distributions that you can read about in your book, and ones that do become important for other statistical techniques. We're going to move on now to what's actually our first bivariate analysis, which means we're taking two variables and describing their relationship to each other. But correlation still kind of falls under the descriptive statistic realm, so we're going to introduce it now and cover it in more depth in week 4 when we start to look at linear relationships between two variables. A correlation is a measure of the linear association between two variables. Correlations between two numeric variables can be explored graphically using a scatter plot. And a correlation coefficient can be calculated to express the strength and direction of an association between numeric variables. You've probably all used the term correlation. You talk about two things being correlated. You say there's a correlation between two phenomenon. And that's a kind of colloquial term that we use. Correlation in the context of statistics has a more specific meaning, particularly when we start talking about correlation coefficients, and we're talking about linear relationships between two variables. So a scatter plot, which is one of my favorite graphs, is where we plot an x and y value. So we've got two different values. We've got an x and a y axis. Here we've got height plotted against weight. So each point represents the combination of height and weight for an individual observation. So if you can imagine a data set where we have person, their height, and their weight, and we're going to plot each point on this graph. Okay, so it can show us the relationship between these two variables in the aggregate. So here we have height plotted on the x-axis, going across horizontally, the y-axis going up. Each dot represents an individual's height and weight. And so it can allow us to visualize the relationship between height and weight. And if your eyeballs aren't seeing a pattern here, it's because this is not a really very strong correlation, although it's a modest correlation. And we can create measures that can quantify what this relationship actually is. You can see here that as height increases on the scale, we're seeing fewer low values, right? So as we move this way, we're generally seeing fewer low values. And as weight increases, notice that we're seeing fewer low values on height. So, okay, so overall, we have a sort of upward linear trend. And as height is increasing, weight is increasing, and vice versa. As weight is increasing, height is increasing. Okay, so there's some relationship between height and weight. We can see that visually, but how can we then quantify that? Well, we could ask the computer to calculate the best fitting line and plot that, okay? And this is zoomed in a little bit, by the way. But we can see here that the points are evenly scattered about this best fitting line, okay? So the way the computer calculates that is it tries to pick that line and rotates that line until it finds the one where if you were to calculate all the differences, it would minimize those differences, okay? So this guy here might be kind of pulling the line up a little higher than it should. But overall, this is the kind of average relationship among height and weight. So that's another way, again, of visualizing the relationship between two variables. We're still not quite at the quantification stage yet. That's where we get to the correlation coefficient. This is a single statistic or numerical value that summarizes the magnitude and direction of a relationship between two variables. And the one that we're going to most commonly report is the Pearson's correlation, or the Pearson's product moment correlation, if we're going to get technical, but we always just call it R, or Pearson's R, is the most widely used correlation coefficient. So Pearson's R is computed with variables that are interval or ratio level measures. There are other correlation coefficients that will allow for other levels of measurement, but Pearson's R is specifically for interval or ratio level measures. Positive values of R, or Pearson's correlation, indicate a positive correlation. As the value of one goes up, the other goes up. They dance together. Negative correlation values, those below zero, indicate a negative or inverse correlation. As the value of one goes up, the other goes down, okay? So we saw that line with height and weight going that direction. It was going the other direction, downward angle. That would suggest that there's an inverse relationship or a negative relationship between height and weight. So the best way to think about this is to visualize it, which we'll do in a moment. But the strength of a correlation is indicated by the absolute value of R, with the values ranging from -1 to 1 and 0 representing no relationship. Okay, so we can describe positive and negative relationships, and the strength is based on the numeric value that we calculate. So a negative 0.75 is just as strong a relationship as 0.75. 0.75 is a strong positive relationship. Negative 0.75 is a strong negative or inverse relationship. Okay. Likewise, a negative 0.75 correlation would be stronger than a positive 0.5 correlation. Because again, the sign is the direction. Are they dancing together, or are they going in opposite directions? And then the magnitude is indexed by the numeric value, where 1 would be perfect correlation, 0 is no correlation. If we get values that are between negative 0.3 and positive 0.3, we would say that there's either a weak relationship or no relationship at all. Okay, and there are rules of thumb for saying how strong a relationship is, and I'll show you visually what these would look like. So we would say a very strong or near perfect positive correlation. This is what an R value of 0.95 would look like. Okay, so let's look at this a little more closely. On the x-axis, as we go higher, we're also going higher on the y-axis, okay? So as the values increase on x, the values increase on y. That's why we have a positive value. And notice how little spread there is here around. You can almost looks like a line, right? So this would be a very, very strong positive correlation. A strong positive correlation would be around 0.80. And here we see there's a little bit of scatter around that best fitting line. It's still moving positive direction, meaning higher values on x correspond to higher values on y. But there's a little bit of noise there in terms of the relationship. A weak positive correlation. Okay, this is similar to what we just saw with height and weight. And if we were to calculate the correlation, it is around 0.4 between height and weight. And we call that a weak positive correlation. Yeah, there's a relationship, but there's probably something else that's explaining each of those values. So height doesn't perfectly explain weight, and weight does not perfectly explain height. So here's 0.40. That's what a positive 0.40 would look like. Negative 0.4, same amount of spread, but in this case, as x increases, as we move up on the x-axis, values are coming down on y. Okay, so when it's angled this direction, that means that as it's going up on x, it's coming down on y. Okay, so notice it's just as strong, just as tight around that line, and that's what a negative 0.4 correlation would look like. A strong negative correlation, negative 0.80, and here would be a perfect negative correlation. All the points are perfectly on that best fitting line. We would rarely find this, and if we did, we would have to assume that we're measuring the same thing just in the opposite directions. This would not necessarily be a desirable thing. It probably means we just had two, let's say, two scales. One case we had, low to high was 1 to 10, and then we flipped it and made it 10 to 1 and correlated, and that would get a perfectly inverse relationship. So, but that's just visually what a perfect correlation. Again, that would be the lowest the correlation could go is 1. The highest it could go would be positive 1. Again, the magnitude is by the numeric value, the sign is the direction of the relationship. So a correlation between two variables implies an association, but not that one variable causes the other. We could have flipped the x and the y axis, although in the case of height and weight, it makes more sense to think of weight as a function of height, which we'll get into later when we talk about linear regression. But when we're doing correlation, we're really more just interested in the relationship, and we should be able to flip x and y axes. The value of R is unitless and is an index of correlation. And we'll see that's kind of an advantage because it allows us to compare variables of all shapes and sizes as far as numeric variables and be able to compare R across different variables. Okay, so it can be interpreted as an average standard deviation change in one variable given average standard deviation change in the other. That's how it's calculated, which we're not going to get into the nitty-gritty on how to calculate R. We let a computer do that for us. But it is really useful because a Pearson's value of 0.50 means that for a 1 standard deviation change in one variable, that corresponds to a 0.5 standard deviation change in the other variable. So again, one reason why we would standardize a variable in the first place is to allow ourselves to compare different variables on different scales. And so 0.50 kind of has a universal meaning in terms of correlation. That's a real advantage of it. It does not depend on the original units to be readily interpretable. A 0.5 correlation is a 0.5 correlation, and it doesn't matter what measures we use. It represents the relationship in standardized units. Comparing values of R across different pairs of variables is meaningful, therefore. So again, don't bog yourself down too much in the calculation, but just think of it as a descriptive measure of how strong a relationship it is between two measures. It's also useful when we want to understand, well, how much of a particular variable have we explained with the other variable? So in the case of height and weight, how much is explained by height when we talk about weight? Well, to do that, we can simply square the value of R, and we call that the coefficient of determination. And it's the proportion of variability in one variable accounted for or explained by a second variable. So if the correlation between height and weight is 0.60, then 36%, so 0.60 times 0.60, 30.36, 36%. 36% of the variability in weight is accounted for by height. Okay, so that's useful information. So about a third, a little more than a third of the variability in weight is predicted by height or is correlated with height. it means there's a lot remaining, though, that we haven't explained. So the remaining variability, which would be 1 minus r squared, mathematically, we don't expect to explain all the variability in complex biological or health-related phenomena, but we do hope to explain as much as we can. So in our prior example, the remaining 64% of variability in weight, not explained by height, is something that we would probably be interested in knowing. And this could be other measurable factors. It could be calorie intake, it could be physical activity level, a whole range of metabolic factors, comorbidities. As we've learned about weight and obesity, we've realized it's much more complicated than we've ever imagined. And so we're never going to be able to fully explain the variability, the human variability in weight. There's going to be some unmeasurable things, even unknown genetic factors and things like that. So we would never seek to 100% explain some phenomenon, but we want to understand as much as we can, because each of those things is contributing information that allows us to better understand some phenomenon. It could also represent error in measurement. Okay, so we're assuming that we've measured these things perfectly, right? But if somebody self-reports height, self-reports weight, okay, there's a tendency to, in case of weight, round down. I'll say I weigh, I'm not gonna say how much I weigh, but let's say I weigh 165 pounds. I might say I weigh 160 pounds. Okay, so we all do that. It's a human tendency to round down, especially with something like weight. So error in measurement could also result in imperfect correlation between two measurements. Okay, so using descriptive statistics, which is what we've covered this week, is an important first step in the research process in getting to know your data. Your choice of descriptive statistics and the graphs we use depend primarily on the level of measurement, but also on the distributions. Measures of central tendency and spread have their advantages and disadvantages, including how easily they are understood. Some of them are probably already familiar to you, others may have been new to you. The ones that are most important are going to be mean and standard deviation as we move forward, but it's important to know these different measures. Correlation analysis is an important descriptive step in understanding linear relationships. As I've mentioned, we're often going to want to invoke other variables to explain some phenomenon, but as a first step, using correlation is a powerful tool to describe those linear relationships. So this wraps up week 1 in terms of lecture. I hope that you will do your reading in chapters 1 through 3, as well as watch the tutorials to help you with your homework, and also to get yourself familiar with the StatCrunch software. So thank you for tuning in, and we'll see you next week when we cover inferential statistics. Have a great week. Bye.